Hello everyone, my name is Saiban Baluka. Today we will discussing an important topic in discrete mathematics and graph theory, which is the Boolean matrix multiplication and reachability matrices. This topic is essential in understanding relation and connectivity in graphs, which have application in computer science and network analysis and more. We will explore two fundamental theorems, learn how to compute powers of matrix using Boolean multiplication, and see how we can determine reachability in graphs. So let's begin. First, let's discuss theorem number 1, which introduced the concept of Boolean matrix multiplication. Suppose we have the relation on a finite set A, we can represent relation using an agency matrix where each element Mij is 1 if there is a direct connection from element Ai to Aj and 0 the otherwise. Now, we define Boolean matrix multiplication denoted by the symbol or the symbol of circ or composed with, unlike the standard matrix multiplication. Boolean multiplication follow these rules. This means that when we compute matrix composed with matrix, we check if there is an intermediate vertex k, such that there exists a path from Ai to k and from k to Aj. So, if such a path exists, we set Mij to number 1. So, this operation helps us find paths of length 2 in a graph. So, let's look at an example to understand this better. In this example, we have an adjacency matrix which represents a relation on a set. We want to compute the m sub r to the squared or m sub r composed with m sub r using Boolean multiplication. Let's analyze the given matrix. To compute the square matrix, we perform Boolean multiplication row by row, checking for intermediate connection. The resulting matrix tells us which elements are connected through an indirect path of exactly 2 steps. As we can see, computing the matrix composed with matrix helps us determine reachability in 2 steps instead of manually searching for paths. This approach scales to longer paths using the same method. Now, let's extend our understanding with theorem number 2, which state that we can compute paths of any length and using Boolean matrix multiplication. Instead of just 2 steps, we can generalize to find paths of any length. Mathematically, this expressed as m sub r to the n equals to m sub r composed with m sub r composed that so on, then compose m sub r n factor. To prove this, we use mathematical induction. The base cases, we already know that P2 is true from theorem number 1. So, the inductive step is if P is true, meaning Mk is equals to matrix composed by M and so on and compose M k factor, then we prove that Pk plus 1 is also true by showing that mk plus 1 equals to mk composed with m. Using this theorem, we can determine whether 2 elements are connected within n step by computing m, and this is particularly useful in computer networks and social graphs where we need to find paths to different length. Now that we can compute paths of length n, let's explore how we determine reachability in a relation. The reachability matrix helps us determine if any element is connected to another by another number of steps. The reachability matrix defined as the star matrix equals to I sub n or matrix or square of matrix or cube of matrix and so on. This means we start the identity matrix, the I sub n, which account for self-looping, then add the matrices M, then square of matrix and cube the matrix, and so on, using the logical OR to accumulate all reachable nodes. Then by computing matrix star, we can determine whether an element X can reach another element Y in any number of steps. This is critical in application like shortest paths, transitive closure, and database queries. Now, we move on to path composition in a graph. To illustrate this, consider a diagram where we are given two paths. Then, path number 1, the 1, 2, 3. Then path number 2, 3, 5, 6, 2, and number 4. By composing these two paths, we get a longer path from node 1 to node 4 with a total length of 6. This example shows how paths combine when we compute higher power of matrix. And to summarize, we explore Boolean matrix multiplication and its role in computing paths in a relation. Then that's all. Thank you for watching. I hope this explanation helps you understand how matrix operation helps us analyze relation and connectivity in a graph. So if you have any questions, feel free to ask. See you next time.